Right now, 1.5 million kilometers from Earth, the James Webb Space Telescope is staring into a region of space so remote that the light reaching it began its journey over 13 billion years ago. Scientists expected to see faint, primitive structures, the cosmic equivalent of childhood photographs. Instead, Webb found something that should not exist: massive, fully formed galaxies blazing with the light of billions of stars, appearing in an era when the universe was supposedly too young, too hot, too chaotic for such structures to form. We're talking about structures containing billions of solar masses appearing just 300 million years after the Big Bang. If the universe were a human lifetime of 80 years, these galaxies appeared when it was less than 2 years old. Dr. Ivo Labe from Swinburne University described the moment of discovery as staring at something that makes you question whether your entire model of reality is fundamentally broken. His team ran the calculations 7 times, convinced there must be an error. There wasn't. Tonight, we're exploring how the most sophisticated telescope ever built discovered something that violates our deepest theories about universal evolution, and what it means when reality refuses to obey the rules we've written for it. Now let's begin. Chapter 1: Golden Vision. The story of the impossible begins with the most sophisticated scientific instrument humanity has ever placed in space. The James Webb Space Telescope isn't just an improvement over previous observatories, it's an entirely different class of cosmic observer designed to see wavelengths of light that have been traveling through expanding space for over 13 billion years. Webb's primary mirror spans 6.5 meters across, composed of 18 hexagonal segments made from beryllium and coated with a microscopically thin layer of gold. This isn't decorative. Gold is the optimal reflective surface for infrared light, the stretched, ancient wavelengths that carry information from the universe's earliest epochs. Each mirror segment was manufactured to tolerances measured in nanometers, polished so precisely that if you scaled one up to the size of the United States, the largest imperfection would be less than 2 inches tall. But size alone doesn't explain Webb's revolutionary capability. The telescope operates at -233 degrees Celsius, kept frigid by a tennis court-sized sun shield that blocks radiation from the Sun, Earth, and Moon. This extreme cold is essential because infrared astronomy requires detecting incredibly faint heat signatures against the cosmic background. Any warmth from the telescope itself would overwhelm the ancient photons it's designed to capture. Webb's location amplifies its advantages. Positioned at Lagrange point 2, it orbits the Sun in gravitational sync with Earth, maintaining a stable observation platform 1.5 million kilometers from our planet. From this vantage point, it can stare continuously at the same patch of sky, for weeks accumulating photons from objects so distant and dim that Hubble's Space Telescope could barely detect them at all. When Webb targets a region of deep space, its 4 scientific instruments begin a carefully choreographed observation sequence. The near-infrared camera captures images across wavelengths from 0.6 to 5 microns. Light that left its source as visible wavelengths but has been stretched by cosmic expansion into the infrared. The near-infrared spectrograph breaks that light into its component wavelengths, revealing the chemical composition, temperature, and motion of distant objects. What makes these capabilities paradigm-shifting is their combination. Webb can see farther into space and therefore backward in time than any previous observatory, while simultaneously analyzing what it sees with unprecedented detail. It's not just taking pictures of the early universe, it's performing spectroscopic autopsies on cosmic history itself. The telescope's first deep-field observation in July 2022 targeted a region called SMACS UP723, exposing for 12.5 hours to capture light from the most distant reaches of observable space. Scientists expected to see primitive proto-galaxies, small, irregular clumps of stars representing the universe's first tentative steps toward structure. The images that emerged told a radically different story. Scattered among the expected faint, smudges were objects that shouldn't exist, bright, massive, well-defined galaxies appearing in an epoch when the universe was supposedly too young to have formed them. The spectroscopic data confirmed these weren't measurement errors or foreground contamination. These were genuine ancient structures, their light redshifted by factors indicating they existed just a few 100 million years after the Big Bang. Dr. Dan Coe from the Space Telescope Science Institute was among the first to analyze these observations. His initial reaction, captured in a video conference that later went viral among astronomers, was simply stunned silence followed by, "These masses can't be right. The universe wasn't old enough." But repeated analysis confirmed the measurements. The galaxies were real, massive, and chronologically impossible according to standard cosmological models. What Webb revealed wasn't a single anomaly, but a pattern. As the telescope surveyed additional fields throughout 2022 and 2023, more impossible galaxies emerged. The Sears survey, targeting the extended Groth strip, found multiple candidates with stellar masses exceeding 10 billion solar masses at redshifts above Z7, meaning they existed when the universe was less than 700 million years old. The GLASS survey identified similar structures. The pattern held across different observation programs, different sky regions, different research teams. The scientific community began using careful language, referring to these objects as galaxy candidates, requiring further confirmation. But as spectroscopic follow-up observations accumulated, the reality became undeniable. These weren't artifacts or misidentifications. They were genuine galaxies, appearing impossibly early in cosmic history, assembled to masses and structures that violated our fundamental understanding of how gravity, matter, and time cooperate to build cosmic architecture. To grasp why this discovery represents such a profound crisis, you need to understand the timeline we thought governed galaxy formation. In the standard cosmological model, the early universe was too hot and energetic for matter to easily clump together. Only after hundreds of millions of years of expansion and cooling could gravity begin pulling hydrogen into the dense clouds that would ignite as stars. Those first stars would then explode as supernovae, enriching space with heavier elements and creating the conditions for the next stellar generation. Galaxies in this model grow gradually through mergers and accretion, small structures combining over hundreds of millions of years to form larger ones. The process is slow, constrained by the speed of gravitational collapse and the cooling rates of gas clouds. To build a galaxy with 10 billion solar masses worth of stars, you need time, lots of time, more time than the early universe supposedly had. Yet here they are, massive, mature galaxies blazing in Webb's infrared images, existing in an era when they have no right to exist. They're not just slightly ahead of schedule, they're impossibly premature, like finding a butterfly emerging from a cocoon that was woven 5 minutes ago. As Webb continues its mission, accumulating more observations across more of the sky, the scope of this problem is expanding. These aren't isolated anomalies confined to one peculiar region of space. They appear to be a fundamental feature of the early universe, suggesting that whatever process assembled them was operating on a cosmic scale with efficiency our models never predicted. The telescope that was supposed to confirm our understanding of cosmic dawn has instead revealed that we've misunderstood something fundamental about how the universe builds galaxies. And that realization is just the beginning of this story. Chapter 2. Impossible Light. The first images from Webb's deep field observations appeared on computer screens at the Space Telescope Science Institute in Baltimore like messages from an alien civilization, comprehensible in format, inexplicable in content. Astronomers saw galaxies, recognized them as galaxies, could measure their properties using standard techniques. But the numbers emerging from those measurements made no sense within the framework of established physics. Galaxy GNZ11, initially detected by Hubble but fully characterized by Webb, emits light that has been traveling for 13.4 billion years. This places its formation at roughly 400 million years after the Big Bang, already pushing the boundaries of what cosmological models predicted. But spectroscopic analysis revealed something more troubling. This galaxy contains an estimated 1 billion solar masses worth of stars, many of them already evolved beyond the first generation. To put this timeline in perspective, consider what had to happen in those first 400 million years. After the Big Bang, the universe was a hot plasma of elementary particles. As it expanded and cooled, electrons and protons combined to form hydrogen atoms, creating the cosmic dark ages, a period when no stars existed to illuminate space. Only after gravity accumulated hydrogen into dense enough clouds could nuclear fusion ignite, creating the first stars. These earlier stars, called Population 3, were massive, short-lived, and composed entirely of hydrogen and helium. They would have lived for only a few million years before exploding as supernovae, enriching the surrounding space with heavier elements. Only then could second-generation stars form, creating the chemical diversity necessary for complex stellar populations and planetary systems. This entire sequence, dark ages, first stars, supernovae, second generation, gravitational assembly into proto-galaxies, merger into larger structures, was supposed to require at least 500 to 700 million years. Yet Webb found completed galaxies at 300 to 400 million years post-Big Bang. The universe would have needed to compress a billion-year process into a few hundred million years, maintaining that accelerated pace across vast regions of space. The key mass measurements are where the impossibility becomes quantifiable. Dr. Ivo Labbé's team at Swinburne University analyzed a galaxy candidate designated Sears 9336, existing at redshift Z16.4, meaning its light comes from just 250 million years after the Big Bang. Spectroscopic data indicated this object contains roughly 100 billion solar masses of material organized into a coherent galactic structure. To accumulate that much mass so quickly, stars would need to form at rates hundreds of times faster than observed in any galaxy in the modern universe. Even if you assume perfect efficiency, every hydrogen atom in a given region converting to stars with no waste, the gravitational timescales don't work. Matter simply cannot fall together that rapidly unless fundamental constants like the strength of gravity or the density of dark matter were radically different in the early universe. What makes these observations particularly disturbing is their consistency. As Webb surveyed different patches of the sky through programs like Sears, GLASS, and JADES, the impossible galaxies kept appearing. They weren't confined to one anomalous region that might indicate a localized oddity in cosmic structure. They're distributed across the observable sky, suggesting that whatever mechanism created them was operating universally during that epoch. The spectroscopic signatures revealed additional mysteries. These early galaxies show evidence of dust, small particles of carbon, silicon, and other heavy elements that can only form through stellar nucleosynthesis and supernova explosions. But dust production requires multiple generations of stars living, dying, and enriching the interstellar medium. The presence of significant dust in galaxies existing just 300 million years post-Big Bang implies an accelerated stellar evolution cycle that current astrophysics cannot explain. Dr. Emma Curtis Lake from the University of Hertfordshire led the spectroscopic confirmation of one of the most distant galaxies, JD's GS Z13.0, at redshift Z13.2. Her team's analysis revealed not just the galaxy's extreme age, but also its chemical composition, elements like oxygen and carbon appearing in abundances that should have required hundreds of millions of years of stellar processing to produce. We're seeing chemical enrichment on timescales that break our models of stellar evolution, Curtis Lake explained in a December 2023 paper. Either stars in the early universe evolved much faster than we understand, or these galaxies somehow contained material that had already undergone processing through multiple stellar generations, which creates an even deeper mystery about where that processing occurred. The morphological structure of these galaxies adds another layer of impossibility. Modern galaxies show clear signs of their assembly history. Irregular dwarf galaxies merge to form larger structures, which eventually settle into the familiar spiral and elliptical shapes we observe today. This process leaves telltale signatures in galactic structure: stellar streams, tidal tails, disturbed morphologies indicating recent mergers. But many of Webb's early galaxies show surprisingly regular, organized structures. They appear as compact, well-defined objects with smooth light distributions, characteristics typically associated with mature galaxies that have undergone significant dynamical evolution. It's as if they skipped the messy adolescence of galactic development and emerged fully formed from the cosmic dark ages. One particularly striking example is a galaxy designated GLASS Z13 observed by the GLASS collaboration. This object exists at redshift Z13, corresponding to about 325 million years post-Big Bang. Yet its morphology suggests a well-established disk structure with organized stellar populations, a configuration that should require billions of years of orbital dynamics to stabilize. The James Webb observations also revealed unexpected star formation rates in these early galaxies. The Alpine collaboration, studying galaxies from this epoch, measured star formation rates exceeding 100 solar masses per year, rates comparable to the most vigorous starburst galaxies in the modern universe. To sustain such prodigious stellar production in the early universe requires gas supplies and accretion mechanisms that cosmological simulations struggle to reproduce. As data accumulated through 2023 and into 2024, the problem only intensified. Each new observation program found additional impossible galaxies. The Primer survey identified candidates at even higher redshifts with even larger masses. The Uncover program revealed early galaxies with complex internal structures and stellar populations, suggesting multiple episodes of star formation, phenomena that should require extended timescales to develop. What emerged wasn't a handful of anomalies that might be explained through exotic but localized circumstances. Webb revealed a systematic pattern. The early universe was far more efficient at forming massive galaxies than our models predict. The discrepancy isn't subtle. These galaxies are orders of magnitude more massive than predicted for their cosmic epoch. Dr. Michael Boylan Colchin from the University of Texas ran detailed simulations attempting to reproduce Webb's observations using standard cosmological models. His results, published in Nature Astronomy, showed that forming galaxies this massive this early would require adjusting fundamental parameters like the efficiency of gas cooling, the rate of stellar feedback, or the clustering properties of dark matter, adjustments so significant that they would break other, well-confirmed predictions of those same models. We can make the models produce one or two massive galaxies at high redshift if we really push the parameters, Boylan Colchin noted. But Webb is seeing an abundance of them, a population of massive galaxies that would require physics we don't currently understand. The light from these impossible galaxies traveled over 13 billion years to reach Webb's golden mirrors, carrying information encoded in their wavelengths about conditions in the universe's infancy. That information is telling us something profound. Our story of how galaxies form is incomplete at best, fundamentally wrong at worst. And this realization is forcing cosmologists to confront an uncomfortable question. If our models fail this? Dramatically, in describing galaxy formation, what else might we have misunderstood about the universe's first billion years? Chapter 3. Broken Rules, the Crisis. James Webb created for cosmology isn't a matter of small adjustments to existing models. These observations break fundamental rules about how matter, gravity, and time interact to build structure in an expanding universe. To understand why astronomers describe this as paradigm-threatening, you need to grasp what those rules are and why they seemed so solid before Webb opened its eye. The standard model of cosmology, called lambda CDM, has been extraordinarily successful for decades. It explains the cosmic microwave background radiation, the large-scale structure of galaxy distribution, the acceleration of cosmic expansion, and countless other observations. This model makes specific, testable predictions about how quickly galaxies can form and how massive they can become at different epochs in cosmic history. Those predictions emerge from fundamental physics. In the early universe, matter existed, primarily as dark matter and ordinary matter in roughly a 5-to-1 ratio. Dark matter, which interacts only through gravity, began clumping under its own gravitational attraction immediately after the Big Bang. These clumps created gravitational wells into which ordinary matter, mostly hydrogen and helium, could fall. But ordinary matter doesn't collapse as easily as dark matter. As gas falls into gravitational wells, it heats up through compression, creating pressure that resists further collapse. Only when that gas can radiate away its thermal energy through emission of photons can it continue collapsing to densities high enough for star formation. This cooling process is governed by the physics of atomic transitions and molecular chemistry, establishing a firm speed limit on how quickly gas can convert into stars. Additional constraints come from stellar evolution itself. The most massive stars burn bright and die young, exploding as supernovae within a few million years. These explosions pump tremendous energy into surrounding gas, heating it and pushing it outward, a process called stellar feedback that actively prevents nearby gas from collapsing into new stars. This creates a self-regulating mechanism. Vigorous star formation triggers feedback that suppresses subsequent star formation, spacing out stellar generations over extended timescales. When cosmologists run computer simulations incorporating all these physical processes, gravity, gas cooling, star formation, stellar feedback, dark matter dynamics, they can predict how quickly galaxies should assemble at different cosmic epochs. These simulations have been refined for decades, tested against observations of nearby galaxies, and validated against lower redshift observations where Hubble could see clearly. Those simulations predict that at redshift Z10, roughly 480 million years post-Big Bang, the most massive galaxies should contain no more than a few billion solar masses. At Z10-12, that limit drops to around 1 billion solar masses. These aren't arbitrary limits, they emerge directly from the time required for gas to cool, stars to form, feedback to regulate, and gravitational assembly to proceed. Webb's observations violate these predictions by factors of 10 or more. Galaxies with 10 to 100 billion solar masses appear at epochs when simulations predict maximum masses of 1 to 2 billion. This isn't a minor discrepancy requiring model fine-tuning. It's a fundamental breakdown of our theoretical framework. Dr. Joel Lager from Pennsylvania State University quantified the problem in a striking way. His team calculated that forming the galaxies Webb observes would require converting essentially all available baryonic matter, every hydrogen and helium atom in a given cosmic volume, into stars with 100% efficiency. In reality, star formation is wildly inefficient. Modern galaxies convert only about 10% of their available gas into stars over billions of years. The early universe would have needed to achieve impossible efficiency on impossibly short timescales. The paradox deepens when you consider dark matter. Galaxies don't just contain stars, they're embedded in massive halos of dark matter that provide the gravitational scaffolding for visible structures. These halos grow through a hierarchical process. Small halos merge to form larger ones, and it's within the potential wells of these halos that baryonic matter can accumulate and form stars. But dark matter halo assembly has its own timescale, governed by the growth rate of density fluctuations in the early universe. Those fluctuations, tiny quantum variations in density from the Big Bang, grow through gravitational instability at a rate determined by the matter density and expansion rate of the universe. You can't arbitrarily speed up this process without changing fundamental cosmological parameters that are tightly constrained by other observations like the cosmic microwave background. Dr. Sandro Teixeira from the University of Cambridge led an analysis attempting to reconcile Webb's observations with theoretical predictions. His team explored every possible adjustment to standard models, increasing star formation efficiency, reducing stellar feedback, accelerating dark matter halo assembly, enhancing gas cooling rates. None of these modifications, even when pushed to extreme values, could reproduce the abundance and masses of galaxies Webb observes without breaking other well-confirmed predictions. "We've tried every knob we can turn in our models," Teixeira explained in a 2023 interview. "Either we're missing entire physical processes that operate in the early universe, or some of our fundamental assumptions about cosmology are incorrect. Neither option is comfortable." The problem extends beyond just galaxy masses. Webb also observes these early galaxies exhibiting substantial dust content and chemical enrichment, signatures requiring multiple stellar generations. But stellar generations take time. A massive star lives for perhaps 10 million years before exploding. The enriched material from that explosion needs time to cool and condense into dust grains. That dust then needs to be incorporated into subsequent generations of star formation. This cycle, star formation, stellar death, enrichment, dust production, next generation, should require at least 100 to 200 million years to produce observable quantities of dust. Yet Webb sees significant dust in galaxies existing just 300 million years post-Big Bang, leaving almost no time for the required stellar cycling. Some researchers proposed that the first stars, population 3 objects composed purely of hydrogen and helium, might have been even more massive than predicted, with masses reaching hundreds of solar masses. Such supermassive stars would have extremely short lifetimes, potentially compressing stellar evolution into shorter timescales. But even optimistic models of population 3 evolution can't compress the timeline enough to explain Webb's observations. Another proposed solution involves primordial black holes. Black holes form directly from density fluctuations in the extremely early universe rather than from stellar collapse. If such objects existed with masses ranging from thousands to millions of solar masses, they could have provided gravitational seeds around which galaxies assembled more rapidly. But primordial black hole scenarios create their own problems, requiring special conditions during cosmic inflation that lack independent evidence. The scientific literature from 2023 and 2024 reflects the community's struggle with these broken rules. Paper after paper proposes modifications, different dark matter properties, varying strength of stellar feedback, alternative modes of rapid gas accretion, even modifications to gravity itself at early times. Each proposal solves some aspects of the problem while creating new conflicts with other observations. What makes this crisis particularly acute is that cosmology prides itself on precision. The lambda CDM model isn't a loose collection of qualitative ideas, it's a mathematically rigorous framework with parameters constrained to a few percent uncertainty by multiple independent observations. When such a precisely defined model fails this dramatically, the scientific foundation feels genuinely shaken. Dr. Priyamvada Natarajan from Yale University, a leading theorist in galaxy formation, captured the moment's significance. We're experiencing something that happens perhaps once a generation in physics, a genuine crisis where observations force us to question bedrock assumptions. This is uncomfortable, exciting, and absolutely necessary for scientific progress. The rules governing galaxy formation seemed ironclad, built on decades of observation and validated through countless tests. James Webb didn't just bend those rules, it shattered them. And that shattering has forced astronomers to consider possibilities that would have seemed absurd just a few years ago, including fundamental revisions to our understanding of the universe's first billion years. Chapter 4. Ancient Monsters Among the Impossible Galaxies. Webb has revealed certain objects stand out as particularly monstrous. Structures so massive and mature that they challenge not just our timeline for galaxy formation, but our understanding of how the universe's largest structures could possibly assemble. Consider Sears 2588, a galaxy observed by the Cosmic Evolution Early Release Science Survey. Spectroscopic analysis places this object at redshift Z sub 7.5, corresponding to roughly 700 million years after the Big Bang. Standard galactic measurement techniques indicate this structure contains approximately 100 billion solar masses, comparable to the Milky Way, a galaxy that has been assembling matter for over 13 billion years. But it's not just the mass that makes Sears 2588 monstrous, it's the organization. Deep imaging reveals a clearly defined disk structure with a prominent central bulge. Morphological features that in modern galaxies result from billions of years of orbital dynamics and stellar migration. The light distribution suggests stellar populations of varying ages, implying multiple episodes of star formation separated by hundreds of millions of years. Yet the universe itself was only 700 million years old when this galaxy existed. To grasp the temporal impossibility, imagine building a medieval cathedral complete with intricate stonework and towering spires in the span of a single afternoon. That's roughly the compression of timescale required to explain Sears 2588's structure within standard cosmological models. Dr. Erica Nelson from the University of Colorado led a detailed analysis of this galaxy's stellar populations. By decomposing its light spectrum into contributions from stars of different ages and compositions, her team reconstructed a star formation history. The results were baffling. The oldest stars in the galaxy appeared to have formed when the universe was only 300 to 400 million years old, with subsequent generations following in rapid succession. We're seeing evidence for sustained, organized star formation over hundreds of millions of years in a galaxy that shouldn't even exist yet, Nelson explained in a February 2024 paper. It's not just that this galaxy is early, it's that it shows evolutionary complexity that requires extended time, but there wasn't extended time available. Another monster lurking in Webb's data is HD1, originally detected by ground-based telescopes but fully characterized by Webb's infrared capabilities. This galaxy exists at redshift Z-13.37, placing it at approximately 330 million years post-Big Bang. Luminosity measurements suggest an ultraviolet brightness requiring either a star formation rate exceeding 100 solar masses per year or the presence of a supermassive black hole with a mass exceeding 100 million solar masses. Both explanations are deeply problematic. Sustaining star formation at 100 solar masses per year requires a continuous supply of cold gas falling into the galaxy at precisely that rate, a delicate balance between gravitational infall and stellar feedback that modern galaxies rarely achieve even over their entire lifetimes. For this to occur in the chaotic early universe, with its extreme temperatures and energetic radiation fields, seems physically implausible. The alternative, a 100 million solar mass black hole, presents even greater challenges. Supermassive. Black holes grow through two mechanisms: accretion of surrounding matter and mergers with other black holes. Both processes take time. Even if HD1 contained a seed black hole from the collapse of a massive early star, growing that seed to 100 million solar masses in just 300 million years requires continuous accretion at near maximum possible rates, the theoretical limit called the Eddington rate. Dr. Fabio Pacucci from the Smithsonian Astrophysical Observatory calculated the requirements for HD1's potential black hole growth. His analysis showed that even starting from an optimistically massive seed black hole of 1,000 solar masses, reaching 100 million solar masses by redshift, Z tau 13 requires accreting matter continuously at or above the Eddington limit for the entire duration. This scenario allows essentially zero downtime, no interruptions from stellar feedback or galaxy interactions, a level of sustained accretion efficiency that seems unrealistic. Black holes in the early universe would have faced massive challenges. To grow this large this fast, Pacucci noted, the very process of accretion generates radiation that pushes matter away, self-limiting growth. Breaking past these limits requires special conditions we don't fully understand. The monster gallery continues with Glass Z12, a galaxy at redshift Z to 12.5, showing a stellar mass exceeding 1 billion solar masses despite existing just 350 million years post-Big Bang. What makes Glass Z12 particularly interesting is its apparent isolation. Unlike many early galaxies that show signs of ongoing mergers or interactions with neighbors, Glass Z12 appears as a compact, well-defined object with no obvious companions. This isolation deepens the mystery of its assembly. Standard hierarchical models predict that massive galaxies at early epochs should show clear evidence of ongoing mergers, the process through which small galaxies combine to form larger ones. The absence of such evidence suggests Glass Z12 assembled through a different mechanism, perhaps through rapid in situ star formation rather than merger-driven growth. But in situ formation of such a massive galaxy in such a short time frame requires even more extreme star formation rates than merger scenarios, rates that would generate stellar feedback powerful enough to blow away the gas supply and shut down further formation. The galaxy exists in a kind of theoretical contradiction, too massive to form through mergers in the available time, but too massive to form through in situ star formation without destroying itself in the process. Dr. Ivo Labé's team identified an entire population of these monster galaxies that they termed universe breakers, a somewhat tongue-in-cheek designation that accurately captures their threat to standard cosmology. 6 candidate galaxies with stellar masses between 10 and 100 billion solar masses at redshifts Z39 to Z11, all existing when the universe was supposedly too young to have built such structures. The term universe breakers reflects a genuine crisis. If these mass measurements are correct, they exceed what the lambda CDM model can produce even under maximally optimistic assumptions. You can't just adjust a few parameters to accommodate them. You need to fundamentally rethink how structure formation proceeds in the early universe. Some of these monsters show additional puzzling features. Several exhibit extremely blue ultraviolet colors, indicating populations of young, hot stars, suggesting ongoing vigorous star formation despite their already enormous masses. This combination of great age to accumulate the mass And youth, indicated by blue colors, creates another temporal paradox. These galaxies simultaneously appear old and young, as if they've been forming stars continuously since impossibly early times. Spectroscopic follow-up of these objects revealed another surprise. Many show emission lines indicating the presence of ionized oxygen and nitrogen, elements that can only form through stellar nucleosynthesis in massive stars and their subsequent supernovae. The presence of these elements in such abundance at such early times implies that multiple generations of stars have already lived and died, enriching the interstellar medium with their products. Dr. Garth Illingworth from the University of California, Santa Cruz, who spent decades studying galaxy evolution with Hubble, described examining Webb's early galaxy data as like discovering that all your assumptions about childhood development were wrong because you found fully formed adults in a nursery. The analogy captures the profound disconnect between expectation and observation. These aren't just precocious galaxies developing slightly ahead of schedule. They're structures that appear to have skipped entire evolutionary phases. The monster. Galaxy phenomenon isn't confined to individual spectacular objects. Statistical analysis of Webb's deep fields reveals an overabundance of massive galaxies across the redshift range, Z7 to Z13. The number density, how many such galaxies exist per unit volume of space, exceeds lambda CDM predictions by factors of 3 to 10 depending on the specific mass range examined. This abundance problem may be even more significant than individual galaxy masses. You might explain one or two extreme objects through rare statistical fluctuations or unusual local conditions. But when massive galaxies appear systematically more abundant than predicted across different regions of the sky, you're observing a population-level phenomenon that indicates something fundamentally different about the early universe's structure. Formation efficiency. Dr. Stephen Finkelstein from the University of Texas, who leads the SEERS collaboration, emphasized this point. Finding one massive galaxy at high redshift would be surprising, but potentially explainable as a rare outlier. Finding dozens of them forces you to conclude that the conditions for rapid galaxy assembly were far more common in the early universe than our models predict. Perhaps most unsettling is what these monsters imply about the invisible infrastructure supporting them. Galaxies don't float in isolation. They reside in halos of dark matter that provide the gravitational scaffolding for visible structures. A galaxy containing 50 billion solar masses of stars likely sits within a dark matter halo containing 500 billion to 1 trillion solar masses of dark matter. But assembling such massive dark matter halos by redshift Z10 or Z12 requires density fluctuations in the early universe that are larger than those measured in the cosmic microwave background. The CMB provides a snapshot of density variations, just 380,000 years after the Big Bang, and those variations appear to be Gaussian random fluctuations with a specific amplitude. Growing those fluctuations into trillion solar mass halos within a few 100 million years exceeds what gravitational instability can accomplish under standard physics. This creates a chicken and egg problem. The galaxies require massive halos to form, but the halos don't have time to grow massive enough to host those galaxies. Either the initial density fluctuations were larger than CMB observations indicate, which would require revising our understanding of cosmic inflation, or dark matter behaves differently in the early universe than current models assume, clumping more efficiently through mechanisms we haven't identified. Some theoretical physicists have proposed that dark matter might undergo self-interactions or phase transitions at high redshifts that enhance its clustering properties. Others suggest that the relationship between dark matter, halo mass, and visible galaxy mass might be fundamentally different in the early universe, with baryonic matter forming stars more efficiently within smaller halos than standard models predict. Each proposal solves aspects of the monster galaxy problem while creating new tensions with other observations. The ancient monsters Webb discovered aren't just curiosities, they're fundamental challenges to our cosmological narrative. They force us to confront the possibility that our understanding of structure formation, validated through decades of lower redshift observations, breaks down completely in the universe's first billion years. And that possibility leads us directly into an even deeper crisis, the timeline of cosmic history itself. Chapter 5. Timeline. Crisis. The monster galaxies. Webb discovered don't just challenge our models of galaxy formation, they threaten the timeline of cosmic history itself. The age of the universe, the expansion rate, the sequence of events from Big Bang to present, all of these carefully calibrated parameters now face scrutiny because the galaxies simply shouldn't be there when they are. Let's establish the timeline we thought we understood. The universe began 13.8 billion years ago. In the Big Bang, a figure determined from multiple independent measurements with a precision of about 1%. For the first 380,000 years, the universe was opaque, filled with hot plasma that scattered photons continuously. Then came recombination, when electrons and protons combined to form neutral hydrogen, allowing light to travel freely for the first time. We see this light today as the cosmic microwave background. After recombination came the cosmic dark ages, a period when no stars existed to illuminate space. The universe contained only neutral hydrogen and helium, slowly collapsing under gravity into denser clouds. Cosmological simulations predict the dark ages lasted until roughly 100 to 200 million years post-Big Bang, when the first stars finally ignited. This event, called cosmic dawn, marks the beginning of the universe's reionization, the process by which starlight ionized the neutral hydrogen filling space. Reionization represents one of the universe's most important phase transitions, transforming the cosmos from neutral to ionized over several hundred million years. The timing and duration of this process are constrained by multiple observations, measurements of distant quasars showing how much neutral hydrogen existed at different epochs, observations of the cosmic microwave background showing when reionization began, and studies of the Lyman alpha forest, absorption features in quasar spectra that reveal the ionization state of intergalactic gas. This entire sequence, dark ages, cosmic dawn, reionization, early galaxy formation, was supposed to unfold over the universe's first 500 to 700 million years, with massive galaxies like those in the modern universe emerging only after about 1 billion years of cosmic evolution. The timeline seemed solid, constrained by both theoretical understanding and observational evidence. Then Webb found fully formed massive galaxies at 300 million years post-Big Bang. Not early prototypes, but structures comparable to mature galaxies. We observe billions of years later. The timeline doesn't just need minor adjustment, it requires complete revision. Dr. Tommaso Treu from UCLA led an analysis examining how Webb's observations conflict with the standard timeline. His team calculated that forming the observed galaxies by their measured epochs would require star formation beginning at redshift Z's to 20 or higher, corresponding to just 180 million years post-Big Bang. But this time frame falls within or immediately after the predicted end of the cosmic dark ages, leaving essentially no buffer period between no stars exist and fully formed massive galaxies exist. We've compressed the entire sequence of cosmic evolution into an impossibly narrow window, Treu explained in a March 2024 paper. First stars, stellar generations, supernova enrichment, galaxy assembly, processes we thought required hundreds of millions of years now need to happen in perhaps 100 million years or less. The compression of this timeline creates cascading problems throughout cosmology. If massive galaxies existed at redshift Z-chart 12 to Z15, they must have contributed significantly to cosmic reionization, the process of ionizing neutral hydrogen in intergalactic space. But reionization's timing is independently constrained by CMB observations from the Planck satellite, which measured the integrated electron scattering optical depth, a quantity that reveals when reionization occurred. Planck's measurements suggest reionization began at redshift Z7 to Z9, corresponding to 650 to 500 million years post-Big Bang. If Webb's massive early galaxies existed hundreds of millions of years earlier, they should have reionized the universe earlier than Planck indicates, unless reionization proceeded in a more complex, extended manner than current models suggest. Either way, our timeline of this crucial cosmic phase transition needs revision. Dr. Renske Smit from Liverpool. John Moores University examined this reionization puzzle in detail. Her analysis showed that the ultraviolet output from Webb's early galaxies, if they were as abundant as observations suggest, would produce enough ionizing photons to reionize the universe significantly earlier than other evidence indicates. This creates a three-way tension between galaxy observations, CMB measurements, and quasar absorption studies, three independent probes of reionization that previously agreed but now appear mutually inconsistent. We have a fundamental timeline conflict, Smit noted in her 2023 analysis. Different observational probes are telling us different stories about when things happened in the early universe. They can't all be right, which means our interpretation of at least one of them is flawed. The timeline crisis extends to the chemical enrichment history of the universe. The metals, astronomers speak, for all elements heavier than hydrogen and helium must be produced in stars and dispersed through supernovae. The abundance of metals at different cosmic epochs serves as a clock for stellar evolution, telling us how many generations of stars have lived and died. Webb's spectroscopy reveals substantial metal abundances in galaxies at redshift Z10 and beyond. Oxygen, carbon, nitrogen, and even heavier elements appear in quantities suggesting significant prior stellar processing. But producing these metals requires time. Massive stars must form, evolve, explode, and enrich the surrounding medium before subsequent stellar generations can form with enhanced metal content. Dr. Tucker Jones from UC Davis calculated the metal production timescales for Webb's early galaxies. His analysis showed that achieving the observed metal abundances by redshift Z10 requires stellar processing rates that exceed anything observed in modern starburst galaxies. Even assuming maximally efficient star formation and supernova enrichment, the timescales are uncomfortably compressed. You need multiple episodes of star formation, supernovae, mixing, and subsequent star formation, a process that normally plays out over 1 billion years, condensed into 300 to 400 million years, Jones explained. The only way to make this work is if stellar evolution proceeded much faster in the early universe than we understand. Some researchers have proposed that the initial mass function, the distribution of stellar masses formed in each star formation event, might have been different in the early universe, weighted more heavily toward massive stars that evolve and explode rapidly. Such a top-heavy IMF could accelerate chemical enrichment, compressing stellar cycles into shorter timescales. But a top-heavy IMF creates its own problems. Massive stars produce copious ultraviolet radiation and powerful stellar winds that heat surrounding gas, inhibiting subsequent star formation. They also produce different ratios of elements than observed in Webb's spectra. While a modified IMF might solve the timeline problem for chemical enrichment, it creates conflicts with other observational constraints. The timeline crisis also affects our understanding of dark matter structure formation. Dark matter halos grow through gravitational instability, with small fluctuations in density gradually amplifying over time. The growth rate depends on the universe's expansion rate and matter density, quantities tightly constrained by CMB observations and large-scale structure surveys. Assembling the dark matter halos needed to host Webb's massive galaxies by redshift. Z12 requires those halos to have grown from density fluctuations present shortly after the Big Bang. But the amplitude of those fluctuations, as measured in the CMB, appears too small to grow into the required halo masses in the available time, unless dark matter clustering proceeds faster than standard cold dark matter models predict. Dr. Sonak Bose from Durham University ran high-resolution simulations examining dark matter halo assembly in the early universe. His results showed that reproducing the abundance of massive halos needed to host Webb's galaxies requires boosting the amplitude of initial density fluctuations by factors of 1.5 to 2 beyond what CMB measurements indicate, a discrepancy that would require revising our understanding of cosmic inflation or early universe physics. We're facing a fundamental tension between early universe observations and late universe structure, Bose noted. The CMB tells us what the density fluctuations looked like when the universe was 380,000 years old. Galaxy surveys tell us what structure exists today. Those two observations are consistent with each other, but Webb's high redshift observations don't fit with either. Perhaps most troubling is what this timeline crisis implies about cosmological parameters. We thought we knew precisely the age of the universe, the Hubble constant describing expansion rate, the matter density. These quantities are interconnected through the Friedmann equations governing cosmic evolution. Adjusting one to accommodate Webb's observations requires adjusting others in ways that create conflicts with independent measurements. Some cosmologists have suggested that the Hubble tension, an existing discrepancy between different measurements of the universe's current expansion rate, might be connected to the galaxy formation timeline problem. If the early universe expanded faster than standard models predict, it would have less time to form structures, but it would also be older at a given redshift, potentially providing the additional time needed for galaxy assembly. But resolving the Hubble tension by modifying expansion history creates new problems for other observations, including the detailed structure of the CMB and the abundances of light elements produced in Big Bang nucleosynthesis. It's like adjusting one corner of a tightly woven tapestry. Pull on it, and the entire pattern distorts. Dr. Adam Rees from Johns Hopkins University, who won the Nobel Prize for discovering cosmic acceleration, characterized the situation. We're seeing multiple cracks appearing in the standard cosmological models simultaneously. The Hubble tension, the early galaxy problem, tensions in the clustering of matter. These might all be symptoms of a deeper issue with our cosmological framework. The timeline of cosmic history, once a source of confident precision in cosmology, has become a battleground where different observations deliver conflicting testimony. Webb's early galaxies aren't just surprising, they're temporally impossible within our established framework. And that impossibility suggests we may have fundamentally misunderstood not just galaxy formation, but the basic chronology of cosmic evolution itself. Chapter 6. Hidden Universe. The crisis James Webb created carries a humbling implication. Despite a century of increasingly sophisticated observations, we may have been blind to major features of the early universe. The cosmos Webb reveals isn't just older than we thought, it's different in character, populated by structures and processes we never predicted because we couldn't see them. This isn't the first time improved observations have revolutionized our cosmic picture. When Edwin Hubble first resolved individual stars in the Andromeda Nebula in 1923, the universe suddenly expanded from our galaxy alone to an immense cosmos containing billions of galaxies. When Vera Rubin measured rotation curves of spiral galaxies in the 1970s, revealing dark matter's gravitational influence, the universe's mass budget transformed overnight. Each observational breakthrough doesn't just add details, it reveals fundamentally hidden aspects of reality. Webb's infrared vision represents this kind of breakthrough. Previous telescopes, including the magnificent Hubble, observed primarily in optical and near-infrared wavelengths. This was adequate for studying nearby galaxies and even relatively distant ones up to redshift Z7 or so. But beyond that frontier, cosmic expansion stretches the light from galaxies so dramatically that their optical emission shifts entirely into the infrared wavelengths, where Hubble's sensitivity dropped sharply. Think of it like trying to study ocean depths with a flashlight that only penetrates a few meters. You might conclude that deep oceans are mostly empty based on what you can see, but the moment someone provides a sonar system, an entirely hidden ecosystem reveals itself. Webb is that sonar system for the early universe, detecting populations of galaxies that were always there but remained invisible to previous instruments. Dr. Caitlin Casey from the University of Texas, who specializes in dusty galaxies at high redshift, described the revelation. "We've been taking a census of the early universe with significant blindness. The galaxies we thought represented the typical population at high redshift might actually be just the tip of a much larger iceberg, the brightest, most extreme objects that Hubble could barely detect." This hidden universe manifests in several ways. First, there's the sheer number of early galaxies. Webb's deep field observations reveal galaxy densities at redshift Z9 to Z13 that exceed previous estimates by factors of 2 to 5. These aren't galaxies we saw poorly before, they're galaxies we couldn't see at all, their light too faint or too redshifted for pre-Webb instruments to register. The abundance implies that galaxy formation in the early universe was far more widespread and efficient than models predicted. Instead of rare islands of star formation scattered in a mostly dark cosmos, the early universe appears to have been buzzing with galactic activity, a busy nursery rather than an empty darkness, with occasional glimmers. Second, Webb revealed a population of dusty galaxies at high redshift that previous surveys missed entirely. Dust absorbs ultraviolet and optical light from stars, reprocessing it into infrared wavelengths. In the local universe, this makes dusty galaxies appear faint at optical wavelengths but bright in the infrared. At high redshift, this dust signature shifts into the wavelength range where only Webb can detect it efficiently. Dr. Pascal Oesch from the University of Geneva led a study identifying extremely red objects in Webb's deep fields, galaxies so dust-obscured that they barely appear in optical wavelengths at all. His team estimates that these dusty galaxies might constitute 30 to 40% of the massive galaxy population at redshift Z7 to Z9, a component completely missed by previous optical surveys. We've been systematically undercounting massive galaxies at high redshift because a significant fraction are hidden behind dust, Oesch explained in a November 2023 paper. This dust bias means our previous understanding of galaxy populations and star formation rates in the early universe was significantly incomplete. The presence of so much dust at such early epochs is itself puzzling. Dust forms from metals produced in stars, so abundant dust requires significant prior stellar evolution. But if dusty galaxies are common at redshift Z8 to Z10, it implies widespread stellar processing hundreds of millions of years earlier, further compressing the timeline of cosmic enrichment. Third, Webb detected a population of faint, compact galaxies that might represent a different mode of early galaxy formation entirely. These objects, too small and faint for Hubble to characterize, show extremely high stellar densities, stars packed into tiny regions with densities thousands of times higher than spiral galaxies like the Milky Way. Dr. Lamia Mola from Wellesley College identified dozens of these ultra-compact galaxies in Webb's Uncover survey. Their compactness suggests they formed through rapid collapse of gas clouds under intense gravitational pressures, or perhaps through early mergers that concentrated stars into small volumes. Either way, they represent a galaxy population whose existence wasn't anticipated by pre-Webb models. These compact galaxies might be the dominant mode of early star formation, small, dense nuggets of stellar activity that later merge and accrete to form the larger galaxies we see at lower redshift, Moeller suggested. If true, we've been missing the foundational building blocks of cosmic structure formation. The hidden universe Webb revealed also includes phenomena at intermediate scales. Between individual galaxies, the telescope detected faint bridges and streams of stars, evidence of ongoing interactions and mergers even at these early epochs. The cosmic web of dark matter filaments that channels galaxy formation appears more active and dynamic in the early universe than simulations predicted, Dr. Danilo Marchesini from Tufts University examined the spatial clustering of Webb's high redshift galaxies. His analysis showed that galaxies at redshift Z9 to Z12 are more strongly clustered, meaning they're found closer together on average than theoretical models predict for that epoch. This stronger clustering suggests the underlying dark matter structure was more developed at early times than we realized, or that galaxies preferentially formed in more extreme density peaks than models assume. The cosmic web architecture appears further along in its development at high redshift than we anticipated, Marchesini noted. Either structure formation proceeded faster than we understand, or galaxies light up in environments different from what we modeled. Perhaps most intriguing are hints that Webb is detecting galaxies at even higher redshifts than officially confirmed. Potential candidates at redshift Z16 to Z20, corresponding to just 200 to 250 million years post-Big Bang. These candidates require spectroscopic confirmation to verify their distances, but if validated, they would push the frontier of observed galaxy formation back even further. Dr. Haojing Yan from the University of Missouri identified several ultra-high redshift candidates in Webb's deep imaging. These objects show extremely red colors consistent with being at redshift Z16 or higher, but they're also surprisingly bright, suggesting either unusually luminous galaxy formation or perhaps entirely new phenomena like population 3 star clusters. That theory predicted, but no telescope has confirmed. We might be on the verge of detecting the first stellar populations, the very first stars igniting in the universe, Yan noted with carefully restrained excitement. If these high redshift candidates are confirmed, we're literally seeing cosmic dawn. The hidden universe isn't just about what we couldn't see before, it's about what we systematically misunderstood. Previous surveys, limited by their wavelength coverage and sensitivity, captured a biased sample of early galaxies, the biggest, brightest, least dust-obscured objects. Based on this biased sample, we constructed models of early galaxy formation that now appear incomplete. Webb's broader wavelength coverage and deeper sensitivity reveal the fuller picture, a picture that's messier, more diverse, and more vigorous than anticipated. Galaxy formation in the early universe wasn't a gradual, orderly process, beginning late and proceeding slowly. It was rapid, widespread, and diverse, with multiple formation modes producing a heterogeneous population of structures. This revelation carries philosophical weight. It suggests that our cosmological models, while mathematically sophisticated and carefully constrained by available data, were fundamentally limited by observational blind spots. We built theories to explain what we could see, not realizing how much remained hidden. Dr. Alice Shapley from UCLA, who has studied galaxy evolution for decades, reflected on this humbling realization. Every major advancement in observational capability reveals how much we didn't know. Webb is teaching us that the early universe was far richer, and more complex than our models suggested, not because those models were stupid, but because they were constrained by incomplete information. The hidden universe Webb revealed doesn't just add details to our cosmic story, it demands fundamental revisions. The early universe wasn't a simple, pristine environment slowly assembling its first structures. It was dynamically complex, efficiently forming diverse galaxy populations under conditions we're still struggling to understand. And that complexity is forcing theorists to develop radically new frameworks for understanding how the cosmos builds. Its structures, frameworks that might require rethinking fundamental physics itself. Chapter 7. Reality Shift. When observational reality contradicts theoretical predictions, this dramatically, science faces a choice. Modify the observations, modify the theories, or modify both. The James Webb discoveries have triggered an explosion of theoretical proposals attempting to reconcile impossible galaxies with physical law. Proposals ranging from conservative model adjustments to revolutionary revisions of cosmological foundations. The most conservative response attempts to preserve standard cosmology while adjusting specific parameters governing star formation efficiency. In lambda CDM models, only a small fraction of available gas converts into stars, typically 5–20% depending on the galaxy mass and environment. This low efficiency reflects the complex interplay of gas cooling, stellar feedback, and gravitational dynamics. But what if star formation efficiency was dramatically higher in the early universe? Dr. Charles Steinhardt from the Cosmic Dawn Center in Copenhagen proposed that reduced metal content in primordial gas might allow more efficient cooling, and thus faster star formation. With fewer metals to produce stellar winds and supernova feedback, gas might collapse into stars more readily, assembling galaxies faster than modern efficiency factors predict. Steinhardt's calculations showed that boosting early star formation efficiency to 40–60%, double or triple modern values, could produce galaxies with stellar masses matching some of Webb's observations. However, this solution struggles to explain the most extreme cases, and it creates tensions with chemical enrichment observations that suggest feedback processes were operating even in early galaxies. A more radical proposal involves modifying our understanding of the initial mass function, the distribution of stellar masses produced during star formation. In the modern universe, most stars are low mass, with only a small fraction becoming massive stars that evolve rapidly. But several theorists have suggested the early universe might have produced a top-heavy IMF, with more massive stars forming per star formation event. Dr. Pratika Dayal from the University of Groningen developed models incorporating top-heavy IMFs at high redshift. Her simulations showed that if the average stellar mass was several times higher in early galaxies, they would produce more light per unit mass, potentially explaining some of Webb's observations without requiring such extreme total masses. However, the top-heavy IMF solution faces significant challenges. Massive stars produce different spectral signatures than low-mass stars, and Webb's spectroscopy doesn't show clear evidence for extreme stellar populations in most early galaxies. Additionally, massive stars produce copious ionizing radiation that should have ionized the universe earlier than observations indicate. Moving beyond star formation physics, some researchers propose modifications to dark matter itself. The standard cold dark matter model assumes dark matter particles move slowly, hence cold, and interact only through gravity. But what if dark matter exhibits additional interactions at high densities or temperatures? Dr. Mark Vogelsberger from MIT explored self-interacting dark matter scenarios where dark matter particles scatter off each other, redistributing energy and potentially accelerating halo formation. His simulations showed that modest self-interaction cross-sections could enhance dark matter clustering at early times, creating more massive halos earlier and thus enabling earlier galaxy formation. Self-interacting dark matter remains speculative. No particle physics evidence supports it, but it demonstrates how revising fundamental assumptions about dark matter's properties might resolve observational tensions. The challenge is that any modification capable of producing Webb's early galaxies must not break the model's success at explaining lower redshift observations. More radically, some cosmologists have proposed revising the cosmic expansion history itself. If the universe expanded slower in its early phases than standard models predict, more time would be available at a given redshift for galaxy formation to proceed. This slower expansion could result from modifying Einstein's equations, introducing new fields or energy components active only at early times. Dr. Mark Kamienkowski from Johns Hopkins University examined such modified expansion scenarios. His analysis showed that a 20–30% slower expansion rate during the first billion years could provide the additional time needed for Webb's galaxies to form without radically changing star formation physics. However, modifying expansion history affects numerous other observables, including the CMB and light element abundances, creating a complex web of constraints. Perhaps the most controversial proposal involves questioning the cosmological principle itself, the assumption that the universe is homogeneous and isotropic on large scales. If the region of the universe we observe has unusual properties, higher than average density, different expansion rate, atypical structure formation efficiency, then Webb's observations might not reflect universal cosmic evolution, but rather local peculiarities. Dr. Subir Sarkar from Oxford University has long questioned the cosmological principle's validity. He argues that if our local cosmic neighborhood sits within a large underdensity or has undergone unusual expansion history, then the standard redshift distance and redshift time relationships might not apply straightforwardly. In such scenarios, galaxies we interpret as being extremely early might actually be somewhat older structures observed under unusual conditions. This direction remains deeply controversial. Abandoning the cosmological principle would require revising foundational cosmological assumptions and reinterpreting decades of observations. Most cosmologists view it as a last resort, to be considered only if all other explanations fail. Some theoretical physicists have even suggested that the galaxy formation crisis might indicate physics beyond the standard model operating in the early universe. Scenarios involving decay of exotic particles, interactions with extra dimensions, or brief periods of modified gravity could potentially accelerate structure formation without leaving obvious signatures in later cosmic evolution. Dr. Abraham Loeb from Harvard University proposed that dark matter might consist of primordial black holes formed in the extremely early universe rather than fundamental particles. If these primordial black holes have masses ranging from thousands to millions of solar masses, they could serve as gravitational seeds around which galaxies assembled more rapidly than in standard scenarios. Primordial black hole dark matter remains speculative. Current constraints from gravitational lensing and other observations limit the allowed mass ranges and abundances. But the Webb crisis has renewed interest in alternative dark matter candidates that might enhance early structure formation. Amid this theoretical ferment, a crucial question emerges. Are we truly witnessing a paradigm-breaking crisis, or might Webb's observations have more mundane explanations? Some researchers caution that measurement uncertainties, systematic errors in distance estimates, or misinterpretation of galaxy properties could be inflating the apparent conflict. Dr. Rachel Somerville from the Flatiron Institute has emphasized the importance of spectroscopic confirmation and detailed modeling before drawing revolutionary conclusions. Photometric redshifts, distance estimates based on colors rather than spectra, can be wrong, especially for unusual objects, she noted. Some of Webb's most extreme galaxy candidates might have more prosaic explanations once we obtain detailed spectroscopy. Indeed, several early Webb galaxy candidates announced as being at extreme redshifts were later confirmed to be at lower redshifts upon spectroscopic follow-up, though they often remained surprisingly massive for their confirmed ages. This pattern suggests that while measurement errors exist, they don't fully explain away the crisis. A genuine excess of massive early galaxies remains even after accounting for misidentifications. The diversity of theoretical responses reflects both the depth of the problem and the uncertainty about solutions. No single modification to standard models cleanly resolves all tensions without creating new conflicts. This pattern, where every proposed solution solves some issues while raising new problems, often signals that multiple revisions might be necessary, or that we're missing some crucial physical ingredient entirely. What's emerging is a humbler cosmology, one that acknowledges profound uncertainties about the universe's first billion years. The Lambda CDM model remains extraordinarily successful at describing cosmic evolution from about 1 billion years post-Big Bang to the present, a 12 billion year span backed by vast observational evidence. But Webb's discoveries suggest this model's extrapolation backward to earlier epochs might be fundamentally flawed. Dr. Michael Turner from the University of Chicago, who coined the term dark energy, characterized the moment we're experiencing the kind of observational theoretical tension that historically precedes major advances. The universe is telling us something important through Webb's observations. Our job now is to listen carefully and follow the evidence wherever it leads, even if it requires revising cherished assumptions. The reality shift Webb triggered isn't just about galaxies, it's about recognizing the limits of our understanding and the need for intellectual humility when confronting a universe that perpetually exceeds our theoretical expectations. And that recognition leads us toward deeper questions about what it means to comprehend cosmic reality at all. Chapter 8: Cosmic Humility. Standing before James Webb's impossible galaxies, humanity faces a moment of profound intellectual humility. Not the false modesty of pretending we know nothing, but the genuine recognition that reality operates on principles we've only partially glimpsed, following rules we've incompletely formulated. This isn't the first time cosmic observations have humbled our cosmic confidence. In the early 20th century, astronomers believed the Milky Way represented the entire universe, a vast but finite island of stars surrounded by empty darkness. Then Edwin Hubble's observations revealed that spiral nebulae were actually distant galaxies, expanding the universe's scale by factors of millions overnight. The cosmos we thought we understood completely turned out to be a tiny neighborhood in an incomprehensibly larger reality. Decades later, Vera Rubin's galaxy rotation curves revealed that 85% of the universe's matter exists in a form we cannot detect directly and don't fundamentally understand dark matter. We built elaborate models describing its gravitational effects, but we remain profoundly ignorant about what dark matter actually is. Our equations work, our comprehension remains shallow. Then came dark energy, the discovery that cosmic expansion is accelerating under the influence of some mysterious energy field permeating space itself. Dark energy constitutes 68% of the universe's total energy content, yet we have essentially no idea what it is or why it exists. We can measure its effects with precision, we cannot explain its nature. Now Webb presents another chapter in this ongoing story of cosmic humility. Galaxies that shouldn't exist appearing when they shouldn't appear, assembled through processes we don't adequately understand. Each revelation strips away another layer of confident certainty, revealing depths we hadn't anticipated. Dr. Martin Rees, Britain's Astronomer Royal, has long emphasized science's provisional nature. Our theories are models, not reality itself. Maps, rather than the territory. When maps prove inaccurate, we revise them. The revision process can be uncomfortable, but it's how science progresses toward better approximations of truth. The discomfort Rees mentions is palpable in the astronomical community. Cosmology spent decades building and refining lambda CDM, achieving remarkable precision in predicting multiple independent observations. The model became not just a framework, but a worldview, a comprehensive story of cosmic evolution from quantum fluctuations to galaxies to the present. Webb's discoveries don't just tweak details of that story, they challenge its foundational narrative. If galaxy formation proceeded fundamentally differently than we understood, what else might our models misrepresent? If the universe's first billion years unfolded through processes we haven't identified, how confident can we be about the subsequent 12 billion years? These questions aren't merely academic, they strike at how science constructs knowledge about domains beyond direct experimental access. We cannot rewind the universe and run the Big Bang again under controlled conditions. We cannot adjust cosmic parameters and observe what changes. We can only observe what actually happened and attempt to reverse engineer the underlying physics. This methodology has been spectacularly successful for much of cosmic history. But Webb's revelations suggest it breaks down in extreme regimes, the universe's infancy, where conditions were so different from anything we can study locally that our theoretical extrapolations fail. We're like investigators trying to understand a complex machine by examining only its mature operational state, missing crucial details about its assembly and early function. Consider what we don't know about the early universe. We don't know the detailed physics of cosmic inflation, the hypothetical exponential expansion that supposedly occurred in the universe's first fraction of a second. We don't know if inflation actually occurred or whether alternative scenarios better describe the universe's origin. We don't know what set the initial conditions for structure formation or why density fluctuations had the specific amplitude observed in the CMB. We don't know the nature of dark matter or dark energy, the components constituting 95% of the universe's content. We've never detected a dark matter particle in laboratory experiments. We have no fundamental theory predicting dark energy's existence or value. These aren't minor gaps. They're gaping chasms in our understanding of the cosmos's basic composition. We don't know if the laws of physics remained constant throughout cosmic history, or whether fundamental constants, coupling strengths, or field interactions evolved with time and temperature. We assume constancy because it simplifies calculations, but we lack observational confirmation across all epochs and regimes. Given these profound uncertainties, perhaps we shouldn't be surprised that predictions about early galaxy formation prove inaccurate. We're extrapolating partial models of incompletely understood processes into domains where we have limited observational constraints, then expressing shock when reality diverges from prediction. Dr. Lisa Randall from Harvard University, a theoretical physicist who studies extra dimensions and fundamental forces, offered perspective. Physics has repeatedly discovered that principles holding inaccessible regimes break down or transform in extreme conditions. Room temperature physics differs from physics near absolute zero. Low-energy particle physics differs from physics at collider energies. Why should we expect physics at redshift z0 to seamlessly extrapolate to physics at redshift z12? This cosmic humility extends beyond acknowledging current ignorance. It requires recognizing that some cosmic truths might remain permanently beyond human comprehension. The universe existed for billions of years before consciousness evolved to contemplate it. It operates on scales from quantum fluctuations to cosmic horizons spanning 60 orders of magnitude. It follows mathematical laws of stunning complexity emerging from principles we've only begun to grasp. There's no guarantee that primate-descended brains evolved to navigate terrestrial environments and social hierarchies possess the cognitive architecture necessary to fully comprehend cosmic reality. We've stretched remarkably far beyond our evolutionary origins through mathematics and observation, but limits likely exist to what biological intelligence can achieve. Yet this recognition
needn't breed despair or resignation.
Acknowledging limits is different from accepting defeat. Science progresses precisely through iterative cycles of prediction, observation, surprise, and revision. Webb's impossible galaxies represent not a failure of science, but its success. The observational capability exceeded theoretical prediction, revealing nature's genuine behavior rather than confirming our expectations. This is exactly what science is designed to do. The humility required here is specific and actionable. It means holding cosmological models more loosely, recognizing them as provisional frameworks rather than final truth. It means designing observations to test assumptions rather than merely confirm predictions. It means celebrating when nature surprises us, because surprises indicate we're learning something genuinely new rather than reinforcing existing beliefs. Dr. Jill Tarter, who spent decades searching for extraterrestrial intelligence, framed this perspective beautifully. The universe doesn't care about our theories. It simply is what it is. Our job isn't to make the universe conform to our models, it's to make our models conform to the universe. When observations and theory conflict, observations win. Always. This principle seems obvious, stated abstractly, but applying it psychologically proves difficult. Scientists invest careers building theoretical frameworks, deriving mathematical predictions, constructing elaborate computational models. When observations threaten those investments, natural human resistance emerges. Careers are built on specific theoretical approaches. Admitting those approaches are fundamentally flawed carries professional costs. The history of science shows that paradigm shifts often require generational turnover, not because older scientists are stupid or stubborn, but because intellectual frameworks become so deeply ingrained that seeing beyond them requires extraordinary cognitive flexibility. Max Planck famously observed that science advances one funeral at a time, a dark joke containing uncomfortable truth about how human psychology shapes scientific progress. But Webb's crisis is unfolding differently because the observations are undeniable and widely replicated. This isn't a subtle effect detected by one research group that others struggle to reproduce. Every team examining Webb's deep fields finds massive early galaxies. The effect is robust, reproducible, and growing more pronounced with additional observations. Reality is forcing revision, whether the community feels ready or not. What makes this moment historically significant is its timing. We're witnessing paradigm shift in real time, documented through papers, conferences, and social media in ways previous scientific revolutions never were. When Hubble discovered cosmic expansion in 1929, news traveled slowly through specialized journals. When Rubin revealed dark matter in the 1970s, the broader public remained largely unaware for years. Now, anyone can watch astronomers grapple publicly with impossible galaxies, proposing and debating solutions in open forums. This transparency reveals science as a profoundly human endeavor. Brilliant people wrestling with recalcitrant data, defending favored theories, slowly converging toward consensus as evidence accumulates. It's messy, contentious, and ultimately self-correcting. The cosmic humility Webb demands extends to you as well. If professional astronomers with decades of training and access to the world's most sophisticated instruments find themselves surprised by the universe's behavior, it's worth asking, what else do you confidently believe that might be wrong? What aspects of reality do you assume you understand that actually remain mysterious? This isn't an invitation to radical skepticism or conspiracy thinking. rejecting all established knowledge because some knowledge proves incomplete. The lambda CDM model remains correct about vast domains of cosmic evolution. General relativity still predicts gravitational waves with stunning precision. Quantum mechanics still explains atomic structure and enables modern technology. Rather, it's an invitation to hold understanding lightly, to remain curious rather than certain, to find excitement rather than threat in discoveries that challenge existing frameworks. The universe revealed by Webb isn't the one we expected, but it's the real one, and therefore more worthy of awe than any theoretical construct. As you go about your life after learning about these impossible galaxies, consider carrying this cosmic humility with you. When you feel certain about how things work, remember that astronomers felt certain about galaxy formation timelines until they didn't. When you encounter information that contradicts established beliefs, remember that the most sophisticated scientific models can require fundamental revision. The universe is under no obligation to make sense to us. It doesn't owe us comprehensibility. The fact that reality has proven partially accessible to human investigation represents a profound gift, perhaps the deepest mystery of all. Why should the cosmos operate according to mathematical principles discoverable by conscious beings? Why should observation and reason reveal anything true about reality? We don't know. We can only remain grateful for the revelations nature provides and humble before the mysteries that remain. Webb's impossible galaxies are teaching us this lesson again, as the universe has taught every generation that looked deeply enough. Reality exceeds imagination, and the cosmos contains depths we've barely begun to explore. Chapter 9. Future Questions. The crisis James Webb created won't be resolved quickly. These aren't puzzle pieces that will snap into place with one brilliant insight or a few more observations. The impossible galaxies represent a frontier where observational capability has outpaced theoretical understanding, opening question spaces that will define astronomical research for decades. The most immediate questions focus on confirming and characterizing Webb's discoveries. While thousands of galaxy candidates at high redshift have been identified through imaging, only a fraction have received detailed spectroscopic confirmation. Spectroscopy provides definitive distances, measures chemical compositions, and reveals kinematics, the motion of gas and stars within galaxies. Each spectroscopic observation takes hours of precious telescope time, but each one transforms uncertain candidates into confirmed measurements. Dr. Roberto Maiolino from Cambridge University leads JADES, one of Webb's largest spectroscopic surveys. His program has already confirmed dozens of galaxies at redshifts beyond Z-10, with plans to characterize hundreds more. Every spectrum we obtain reveals new puzzles, Maiolino explained in a recent presentation. We're not just confirming distances, we're discovering that these early galaxies have properties we never predicted. Chemical abundances that don't fit models, kinematics suggesting rapid rotation, emission lines indicating exotic ionization conditions. The coming years will see systematic spectroscopic campaigns targeting Webb's galaxy candidates, building statistical samples large enough to distinguish between different theoretical explanations. Is the overabundance of massive galaxies real, or partly an artifact of photometric distance estimates? Do these galaxies show consistent properties suggesting a universal formation mechanism, or diverse characteristics indicating multiple pathways? To early mass assembly, beyond confirmation, Webb's ongoing observations continue pushing toward higher redshifts. The telescope has already detected plausible candidates at Z-16 to Z-20, the very edge of cosmic dawn when the first stars ignited. If confirmed, these objects would provide direct observations of the universe's transition from darkness to light, revealing how stellar ignition began and spread through primordial gas. Dr. Garth Illingworth, who has spent decades studying distant galaxies, describes the search for cosmic dawn as astronomy's holy grail. We're trying to witness the moment when the universe woke up, when the first light broke through primordial darkness. Webb has the capability to see this transition directly, observing the very first stellar populations and the galaxies they assembled into. But observing cosmic dawn requires more than just detecting faint objects. It requires understanding what you're seeing, distinguishing between different stellar populations, measuring ionizing photon production rates, tracing how ionization progressed region by region across the cosmos. These measurements demand exquisite sensitivity and careful analysis, pushing Webb's capabilities to their limits. Another crucial question involves understanding what we're missing. Webb observes in infrared wavelengths from 0.6 to 28 microns. But even longer wavelengths, the far infrared and submillimeter, remain largely unexplored at high redshifts. The Atacama Large Millimeter Array, ALMA, observes these wavelengths from the ground, but its sensitivity for distant galaxies is limited. Dr. Alexandra Pope from the University of Massachusetts studies dusty star-forming galaxies that emit most of their light at far infrared wavelengths. She emphasizes that current observations likely miss a significant population. The dustiest, most heavily obscured galaxies at high redshift might be essentially invisible to Webb because their light is absorbed and re-emitted at wavelengths
Longer than Webb can detect, we need next-generation far-infrared space telescopes to complete the census.
Future missions like the Origin Space Telescope, still in conceptual design phases, would observe far infrared wavelengths from space, potentially revealing another hidden galaxy population. The combination of Webb's near to mid-infrared observations with far infrared coverage would provide the most complete picture of early galaxy formation possible. Theoretical work faces equally pressing questions. Can Lambda CDM be modified to accommodate Webb's observations without breaking its successes?
At lower redshifts?
What physical processes might operate in the early universe that our models currently neglect? How can simulations be improved to better predict high redshift galaxy properties? Dr. Rachel Somerville leads efforts to enhance galaxy formation simulations with more sophisticated physics. Her team is incorporating better models of stellar feedback, magnetic fields, cosmic ray pressure, and turbulence, physical processes that might significantly affect early galaxy formation but are computationally expensive to simulate accurately. The simulations we ran to predict what Webb would see were state-of-the-art, but they still simplified or neglected many physical processes, Somerville noted. Now we're working to include more complete physics, testing whether improved simulations can reproduce observations without requiring fundamentally new cosmology. This simulation work connects to deeper questions about dark matter and dark energy. If standard cold dark matter cannot produce the observed early galaxy abundance, what alternatives might work? Warm dark matter, which moves faster than cold. Dark matter, and suppresses structure formation on small scales, seems unlikely given that Webb sees abundant small galaxies. Self-interacting dark matter, fuzzy dark matter, and various exotic alternatives all have proponents exploring their implications. Similarly, dark energy's properties remain mysterious. Could dark energy have been different in the early universe, weaker, or even negative, allowing faster structure formation? Such dynamical dark energy models face tight constraints from other observations, but Webb's discoveries add motivation for exploring non-standard cosmological scenarios. Some of the most speculative questions venture into fundamental physics. Could the fine structure constant or other physical constants have been different in the early universe, altering stellar evolution timescales? Might extra dimensions predicted by string theory have affected gravitational dynamics during structure, formation, Could the universe have undergone phase transitions in its first billion years that left subtle signatures in galaxy properties? These questions push beyond astronomy into theoretical physics, requiring collaboration between observers, cosmologists, and particle physicists. Webb's discoveries are forcing conversations across disciplinary boundaries, uniting researchers who normally work in separate domains. Dr. Lisa Randall emphasized this interdisciplinary necessity. Understanding the early universe requires bringing together cosmology, astrophysics, and fundamental physics. The impossible galaxies Webb found might ultimately require new physics, not just astrophysical process adjustments, but genuine extensions to the Standard Model or modifications to general relativity. Practical questions also emerge about how to continue this research. Webb represents a decade-long development process and a $10 billion investment. It's revolutionizing our understanding, but it's also the only instrument of its kind. What happens if it fails? How do we maintain progress if Webb's mission ends before questions are answered? The astronomical community is already planning Webb's successors. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will survey vast areas of sky, complementing Webb's deep but narrow observations. Ground-based extremely large telescopes like the European ELT and Giant Magellan Telescope, with mirrors 25 to 30 meters across, will provide complementary capabilities from Earth's surface. But the ultimate successor to Webb for studying the early universe would be a larger, more sensitive infrared space telescope. Concepts like the Habitable Worlds Observatory or LUVOIR, Large UV Optical IR Surveyor, have been proposed, though they remain decades from potential launch. These future instruments would have collecting areas several times larger than Webb, able to study early galaxies in far greater detail. Dr. John Mather, Webb's senior project scientist and Nobel laureate, reflects on the long timelines. We start planning major space telescopes 20 to 30 years before they launch. Webb was proposed in 1989 and launched in 2021. The next comparable mission might not fly until the 2040s. This means the questions Webb is raising today might not be fully answered for another generation. This temporal reality shapes how current researchers approach Webb's discoveries. The impossible galaxies they're studying now will define careers, inspire doctoral theses, and motivate theoretical developments for decades. The resolution of this crisis, whatever form it takes, will emerge gradually through accumulated observations, refined models, and perhaps paradigm shifts we cannot yet imagine. But even as specific questions about early galaxies eventually find answers, deeper mysteries remain. Why does the universe permit galaxy formation at all? Why do the fundamental constants have values that allow complex structures to exist? Why does the cosmos appear comprehensible to conscious observers that evolved within it? These ultimate questions transcend astronomy, touching philosophy, metaphysics, and the deepest puzzles of existence itself. Webb's discoveries don't answer them, but they remind us that such questions remain vital, that the universe continues, surprising us, and that human curiosity finds its fullest expression in pursuing understanding, even when comprehension seems forever beyond reach. Chapter 10: Eternal Mystery. We began this journey with James Webb's shocking discovery. Galaxies that shouldn't exist appearing when they have no right to appear, assembled through processes we don't adequately understand. We've traced the crisis from first detection through theoretical chaos, examining how observation shattered prediction and forced cosmology to confront fundamental uncertainty. But perhaps the deepest revelation isn't about galaxies at all, it's about the relationship between human knowledge and cosmic reality. We've spent this entire exploration documenting what we don't know, cataloging failures of understanding, and acknowledging profound mysteries. Yet somehow, despite all this ignorance, we can see 13 billion years into the past and recognize that what we're seeing violates our expectations. This ability itself is extraordinary. Consider what had to happen for you to learn about impossible. Galaxies tonight. Photons emitted by stars forming in the early universe traveled through expanding space for over 13 billion years. They entered a telescope positioned 1.5 million kilometers from Earth, reflected off gold-coated mirrors manufactured to nanometer precision, and struck infrared detectors cooled to near absolute zero. Those detectors converted photons into electrical signals, which were processed by computers, transmitted across space to Earth, analyzed by scientists who spent decades learning to interpret spectroscopic data, and ultimately synthesized into images and measurements that reveal cosmic history. This entire chain, from ancient starlight to your comprehension, represents an almost miraculous convergence of natural law, technological achievement, and human curiosity. The fact that any of this works remains deeply puzzling. Why should the universe operate according to mathematical principles? Why should those principles be discoverable through observation and reason? Why should physical laws remain consistent across billions of years and billions of light years, allowing us to interpret ancient light using physics measured in laboratories today? We don't know. These questions venture beyond science into philosophy, probing the mysterious relationship between mind and cosmos. The physicist Eugene Wigner famously described the unreasonable effectiveness of mathematics in the natural sciences. The strange fact that mathematical structures invented by human minds for abstract purposes somehow perfectly describe physical reality. Webb's impossible galaxies participate in this deeper mystery. Yes, they violate lambda CDM predictions, creating a crisis for cosmology, but they also demonstrate that reality has a coherent structure we can partially access despite our limitations. The galaxies are impossible according to our models, yet they follow some logic, some deeper set of principles we haven't grasped but might eventually discover. This tension between knowledge and mystery defines the human relationship with the cosmos. We know vastly more than our ancestors: the age of the universe, its composition, the laws governing stellar evolution, and galactic dynamics. Yet every answer reveals new questions. Every solved mystery opens onto deeper mysteries. Understanding never reaches completion. It only expands the boundary of known ignorance. Dr. Maria Spiropoulou from Caltech, a particle physicist who studies dark matter, captured this paradox. The more we learn, the more we realize how much remains unknown. But this isn't frustrating, it's thrilling. Each discovery is both an answer and an invitation, resolving immediate questions while revealing profound, new puzzles. The impossible galaxies Webb found invite us into exactly this relationship with cosmic mystery. They answer questions about whether massive galaxies existed in the early universe. Yes, they did. But they immediately raise deeper questions about how such galaxies form, what processes we're missing, whether our cosmological framework is fundamentally incomplete. You're living through a moment of genuine scientific revolution, watching in real time as observations force paradigm reconsideration. Most people never witness such moments. The last comparable crisis in cosmology occurred in the late 1990s with dark energy's discovery over 25 years ago. Before that, dark matter in the 1970s. Before that, cosmic expansion in the 1920s. These transformational discoveries arrive, perhaps once per generation. What makes this moment special is its accessibility. Webb's images are public, released hours after processing. Research papers appear on open preprint servers immediately upon submission. Scientists discuss findings on social media and in YouTube videos. You don't need institutional access or specialized training to witness this revolution. You can watch it unfold alongside professional astronomers. This transparency reveals science not as a collection of settled facts dispensed by authorities, but as an ongoing human struggle to comprehend reality. You've seen throughout this exploration how astronomers grapple with recalcitrant data, propose competing explanations, and slowly converge toward better understanding through observation and debate. This process is science's true nature: messy, contentious, self-correcting, and ultimately successful at approaching truth. The impossible galaxies also offer perspective on your place in cosmic history. You exist 13.8 billion years after the Big Bang, in an era when the universe has expanded to vast scales, cooled to near zero temperatures, and assembled structures of stunning complexity. Consciousness emerged from stellar nucleosynthesis. You are literally made of star stuff, atoms forged in nuclear furnaces and dispersed through supernovae. Those atoms, governed by quantum mechanics and organized through chemistry, somehow assemble into structures capable of contemplating their own origins. Your brain contains more neurons than there are stars in a typical galaxy, connected in networks of staggering complexity. Through this biological computer, you can understand, at least partially, how galaxies form, how stars evolve, how the universe expands. This ability to comprehend cosmic history represents perhaps the universe's most remarkable achievement. For 13.8 billion years, matter evolved from elementary particles to atoms, to molecules, to stars, to galaxies, to planets, to life, to consciousness. And now, through consciousness, the universe contemplates itself, matter examining its own history and nature. When you look at Webb's images of impossible galaxies, you're participating in cosmic self-awareness. Those galaxies existed long before Earth formed, before the sun ignited, before biological life emerged. Yet here you are, billions of years later, on a small planet orbiting an ordinary star, able to detect their light and ponder their significance. This capacity for cosmic comprehension seems wildly improbable, a fluke of evolutionary history that happened to produce brains capable of abstract reasoning and mathematical thinking. Yet here we are, generation after generation, pushing the boundary of understanding further, building instruments that extend our senses across electromagnetic spectrum and cosmic distance. Throughout human history, our cosmic perspective has undergone radical transformations. Ancient civilizations believed Earth sat at the center of creation, with celestial spheres revolving around our privileged location. This geocentric model wasn't ignorance, it was a reasonable interpretation of observable phenomena. The ground beneath our feet feels stationary. The sun appears to circle overhead, stars wheel across the night sky in predictable patterns. Then Copernicus, Galileo, and Kepler revealed that Earth orbits the sun, not the reverse. This heliocentric revolution displaced humanity from cosmic center stage, but we still believed our sun might be unique, perhaps the only star, certainly the most important object in existence. Spectroscopy, in the 19th century, revealed that stars are distant suns, each potentially hosting its own system of worlds. Suddenly the universe expanded from a solar system to a galaxy containing hundreds of billions of stars. Yet even this vast expansion left us thinking the Milky Way constituted the entire universe. Hubble's observations in the 1920s shattered that comfortable assumption. Those fuzzy nebulae weren't gas clouds within our galaxy, they were entire galaxies, island universes separated by millions of light-years of space. The cosmos exploded in scale by factors of millions, and humanity's cosmic address changed from center of everything to one planet, orbiting one star in one galaxy,
among billions.
Each of these revolutions followed a pattern: confident understanding, shocking observation, paradigm crisis, theoretical revision, new understanding, until the next shocking observation begins the cycle again. Webb's impossible galaxies fit perfectly into this historical pattern. We thought we understood galaxy formation. We built sophisticated models validated by decades of observations. Then a more powerful instrument revealed we'd been systematically wrong about a fundamental aspect of cosmic evolution. This pattern suggests a profound truth. Our understanding of the universe will always be incomplete. Not because humans are stupid or science is flawed, but because reality contains infinite depths that any finite investigation can only partially explore. Each generation of instruments reveals phenomena invisible to previous technology. Each theoretical framework eventually encounters observations it cannot explain. When we call Webb's galaxies impossible, we're making a specific claim. They're impossible according to Lambda CDM, our current best model of cosmic evolution. But the galaxies clearly exist. The light reaching Webb's detectors is real. The spectroscopic measurements confirming their distances and masses are genuine. So what does impossible actually mean in this context? It means our map doesn't match the territory. The models we constructed to explain galaxy formation failed to predict what actually happened in the early universe. This failure doesn't make the galaxies impossible, it makes our models incomplete. This distinction matters because it preserves the rational foundation of science while acknowledging its limitations. We're not claiming the universe violates logic or that physical law breaks down. We're recognizing that our current formulation of physical law doesn't capture all relevant phenomena. Something is missing from our models: additional physics, overlooked processes, misunderstood parameters. The search for that missing element drives contemporary research. Every proposed solution to the impossible galaxy problem, whether it's modified star formation, exotic dark matter, alternative cosmology, or something else entirely, represents an attempt to expand our models to accommodate reality. This is precisely how science progresses. Observation contradicts theory, forcing theoretical revision that better captures natural phenomena. Dr. Sandra Faber from UC Santa Cruz, who has spent 6 decades studying galaxies, offered this perspective. I've watched galaxy formation theory evolve through multiple crises. Each time we thought we understood, new observations revealed our understanding was shallow, but each crisis led to deeper models that explained more phenomena. Webb's discoveries will do the same. They'll force us toward better theory. This optimism isn't naive. It's grounded in science's historical track record of converting impossible observations into understood phenomena through persistent investigation and theoretical creativity. Hubble's cosmic expansion seemed impossible, according to static universe models, until it prompted development of Big Bang cosmology. Supernova observations showing cosmic acceleration seemed impossible according to matter-only models, until they prompted recognition of dark energy. Webb's impossible galaxies will likely follow the same pattern. The current confusion will give way to revised models that explain early galaxy formation more accurately. Those models might require new physics, or they might simply require better application of known physics in extreme conditions. Either way, impossibility will transform into understanding. But even as specific puzzles find solutions, deeper mysteries remain. The impossible galaxies raise questions that transcend astrophysics, touching the foundations of existence itself. Why does the universe permit structure formation at all? Why do physical constants have values that allow complexity to emerge? Why does consciousness exist to contemplate these questions? These ultimate questions have occupied philosophers and theologians for millennia, and they remain as mysterious today as ever. Science can describe how galaxies form, or at least is working towards such description, but it cannot explain why. The universe is such that galaxies can form. It can trace consciousness back to neural activity, but it cannot explain why neural activity feels like something from the inside. Perhaps these deepest questions admit no scientific answer. Perhaps they lie forever beyond empirical investigation, accessible only through philosophical speculation or spiritual intuition. Or perhaps they're simply questions we haven't yet learned how to ask properly, awaiting future frameworks that dissolve current confusions. Whatever the case, learning to live with mystery, with permanent, irreducible unknowing about fundamental aspects of reality, represents a form of wisdom. It's the recognition that comprehension has limits, that uncertainty is not a temporary condition awaiting resolution, but a permanent feature of the human relationship with cosmos. This wisdom doesn't require abandoning the quest for understanding. You can pursue knowledge vigorously while accepting that complete knowledge remains forever beyond reach. You can celebrate scientific progress while acknowledging that progress reveals as much new mystery as it resolves. The impossible galaxies exemplify this dual nature of discovery. They represent both knowledge. We now know massive galaxies existed far earlier than predicted, and mystery. We don't know how they formed or what this means for fundamental physics. Every answer contains questions. Every solution opens new puzzles. Perhaps the deepest revelation isn't about galaxies at all. It's about the relationship between human knowledge and cosmic reality. We've compressed billions of years of cosmic evolution into mathematical models, traced galactic assembly across cosmic time, and built instruments capable of detecting light that has traveled for most of the universe's existence. Yet despite these extraordinary achievements, we remain fundamentally ignorant about basic aspects of reality. We don't know what dark matter is. We don't know why dark energy exists. We don't know if our universe is alone or part of a vast multiverse. We don't know why physical laws take the forms they do, or whether they could have been different. Living with this profound ignorance while continuing to pursue understanding requires a particular kind of intellectual courage, the willingness to acknowledge how little we know while persisting in the effort to know more. It's the courage to build models knowing they'll eventually prove inadequate, the courage to make predictions, knowing observations might contradict them, the courage to invest careers in theories that reality might overturn. Webb's impossible. Galaxies demand exactly this courage. They force astronomers to acknowledge that decades of galaxy formation theory missed something fundamental. They require theorists to question assumptions they've treated as bedrock. They push the entire field toward uncomfortable uncertainty about phenomena we thought we understood. But this discomfort is precisely where scientific progress happens, in the tension between expectation and observation, in the struggle to reconcile theory with data, in the creative chaos that follows paradigm-shattering discoveries. The impossible galaxies aren't a problem to be solved and forgotten. They're an invitation into deeper understanding, a reminder that reality always exceeds our models of it, and a promise that the universe will never stop surprising those bold enough to look carefully. As you carry the knowledge of these impossible galaxies forward, remember that you're part of a species that asks questions about its own origins, builds instruments to peer across billions of years, and refuses to accept ignorance as permanent. You're made of star stuff contemplating stars, organized matter examining the principles of its own organization, consciousness puzzling over the mystery of its own existence. The galaxies James Webb found are impossible, but they exist. And in that paradox lies everything worth knowing about the relationship between human understanding and cosmic reality. Throughout this journey into the impossible, we've discovered how James Webb's golden mirrors revealed galaxies that violate our cosmic timeline, massive, mature structures appearing just 300 to 400 million years after the Big Bang, when the universe should have been too young, too hot, and too chaotic for such formations to exist. We've traced how these observations shattered the Lambda CDM model's predictions, creating a genuine crisis in cosmology as decades of carefully constructed theory collided with undeniable observational reality. We explored the monster galaxies, lurking in Webb's data, structures containing tens to hundreds of billions of solar masses, exhibiting organized morphologies and chemical enrichment that should require billions of years to develop, yet appearing when the universe was less than 5% of its current age. We saw how these discoveries compressed the timeline of cosmic evolution into an impossibly narrow window, forcing theorists to question fundamental assumptions about star formation efficiency, dark matter properties, and even the expansion history of the universe itself. We confronted the hidden universe that previous telescopes couldn't see, populations of dusty, compact, and ultra-distant galaxies that were always there but remained invisible until Webb's infrared vision revealed them. These hidden populations doubled or tripled our estimates of early galaxy abundance, demonstrating how observational blind spots had systematically biased our understanding of cosmic dawn. We witnessed the reality shift as cosmologists proposed, increasingly radical solutions, modified star formation physics, alternative dark matter models, revised expansion histories, and even questioning the cosmological principle itself. Each proposed solution reveals both the depth of the crisis and the creativity scientists bring to reconciling observation with theory. But perhaps the most profound revelation has been about cosmic humility, recognizing that despite a century of increasingly sophisticated observations and mathematically rigorous models, we've fundamentally misunderstood something essential about how the universe builds its largest structures. This humility isn't defeat. It's the honest acknowledgement that reality operates on principles we've only partially glimpsed, following rules more subtle and complex than our current frameworks capture. As you go about your day after watching this, consider that you're living through a pivotal moment in humanity's cosmic story. The James Webb Space Telescope isn't just taking pretty pictures, it's forcing a scientific paradigm to confront its failures and evolve toward deeper understanding. You're witnessing the same kind of revolution that occurred when Hubble discovered cosmic expansion, or when Rubin revealed dark matter, moments when observation shatters certainty and opens new frontiers. When you look at the night sky, remember that those distant points of light carry information about cosmic history stretching back billions of years. Some of the photons entering your eyes began their journey when the universe was unimaginably different, hotter, denser, younger. Webb has taught us that era was also more complex, more active, and more mysterious than we ever imagined. Remember, too, that you are part of this cosmic story. The atoms composing your body were forged in stellar cores and dispersed through space by supernovae. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created through nuclear fusion in stars that died billions of years ago. You are literally made of ancient stardust, organized through chemistry and biology, into a structure capable of understanding its own origins. This connection between you and the cosmos isn't metaphorical or spiritual, it's physical and direct. The same laws governing galaxy formation also govern the chemistry of your cells. The same quantum mechanics describing atomic structure in Webb's distant galaxies also enables the neural processes underlying your thoughts right now. You aren't separate from the universe, contemplating it from outside. You're the universe examining itself. Matter evolved to consciousness, pondering its own nature. The impossible galaxies Webb discovered remind us that this self-examination is ongoing, incomplete, and endlessly fascinating. Every answered question reveals new mysteries. Every solved puzzle opens onto deeper complexities. The universe will always exceed our models of it, not because those models are worthless, but because reality is inexhaustibly rich. This inexhaustibility is gift, not burden. A fully understood universe would offer no mysteries to inspire wonder, no unknowns to motivate exploration, no frontiers to challenge human curiosity. The fact that cosmic reality perpetually surprises us, that telescopes keep finding impossible things in impossible places, ensures there will always be new questions to pursue, new observations to make, new understanding to develop. So when you encounter certainty in your own life, moments when you think you fully understand how something works or why something is, remember these impossible galaxies. Remember that the most sophisticated scientific minds, armed with the most powerful instruments and most precise mathematical models, discovered they'd fundamentally misunderstood galaxy formation. If cosmology can be that wrong about something so central, perhaps humility is warranted in all human endeavors. But remember also that this humility doesn't prevent understanding, it enables it. By acknowledging what we don't know, we create space for better knowledge to emerge. By accepting that our models are provisional, we remain open to observations that challenge them. By embracing uncertainty, we position ourselves to learn from reality rather than forcing reality to conform to our expectations. If you made it this far through this exploration of cosmic impossibility, subscribe and give a thumbs up. And check out my video on dark matter's mysteries. After learning about impossible galaxies, you'll appreciate how dark matter itself might be even stranger than we currently imagine. The link is in the description. The James Webb Space Telescope will continue operating for years, accumulating more observations, finding more impossible things, pushing deeper into cosmic history. Each new discovery will refine our understanding, resolve some mysteries while revealing others, slowly constructing a more accurate map of the universe's first billion years. But no matter how complete that map becomes, reality will retain its essential mystery, the wonder that anything exists at all, that consciousness emerged to contemplate existence, that matter organized itself into structures capable of understanding physical law. These deepest questions will remain even after the impossible galaxies are explained, reminding us that science's greatest achievement isn't eliminating mystery, but revealing how profound and beautiful mystery can be. Right now, 1.5 million kilometers from Earth, Webb stares into deep space, collecting ancient photons that began their journey over 13 billion years ago. Those photons carry stories of impossible galaxies, cosmic dawn, and a universe more wondrous than prediction imagined. And you, made of star stuff, equipped with consciousness, living at the precise moment in history when technology enables seeing cosmic birth. You get to witness these revelations, participate in this ancient human quest to understand the cosmos, and marvel at how reality perpetually, beautifully, impossibly exceeds expectation.